Okay, next up is scalars and vectors. This is a topic that you're going to come back to over and over again whilst doing any mechanics topics. You're also going to meet this in maths as well, so you'll get a good chance to go over it again. But the sooner you get it right, the easier life will be. So, let's get down to it. Things that I'm going to want you to be able to do. You need to be able to give examples of scalars and vectors. This is a really common sort of 1 or 2 mark question at the beginning of exams, giving examples of scalars and vectors. You need to be able to add and subtract scalar and vector quantities. Scalar one's easy. You need to be able to use vector triangles to determine the resultant of any 2 coplanar vectors. Coplanar just means that they are in the same plane. So imagine that they are either left to right or up and down, so that you could put an edge of a paper along them from one to the other. That would be a plane. And finally, resolving vectors into 2 perpendicular components. So if I'm determining the resultant, I'm adding 2 together. If I'm resolving, I'm kind of taking one and splitting it into 2. But it's easier when you see it. So we need to make sure that we know what scalars and vectors are. So you should already know. So just take a second for yourself, have a ponder. What is the difference between a scalar and vector? Feel free to pause, say it out loud, then you can be vindicated in a second. So, scalar quantities are quantities that only have a magnitude. Vector quantities are quantities that have both a magnitude and a direction. So they're quantities where direction matters. So, let's have a look at some examples. So our first one is mass. So, is mass scalar or vector? Does its direction matter? Well, no, it doesn't. It doesn't matter at all. It's just an amount. If I'm asking your mass, I don't ask you what's your mass at 45 degrees to the ground. That doesn't make any sense. So it's definitely a scalar quantity. Weight, on the other hand, hopefully we do know that there's a difference between weight and mass. So weight, its direction does matter because weight is the force of gravity acting on your mass. And that's got to be acting towards, if we're on Earth, the centre of the Earth. So its direction does matter because it's a force. So it is in fact a vector quantity. Next up is speed. Speed is just the rate at which your distance is changing. So distance over time. That is a scalar. Next up we've got velocity. Velocity is different. Velocity is the rate at which your displacement changes per second. So that's your distance from a certain point. Now if it's from a certain point, then your direction really does matter. So velocity is in fact a vector. Force, hopefully you're all sat there going, well, I've just done weight, so this is easy. This is also a vector quantity. Next we've got pressure. Aha, what do you think of this one? Pressure is scalar because it doesn't matter about the direction at all. Next up is electric current. May or may not know this one, but it is a vector because it has a direction. The current flows one way around the circuit, the other way around the circuit. And it matters because some components only work if the current is going the correct way through them. Next up is temperature. Hopefully we all know temperature is just a scalar quantity. There is no direction of temperature. It's just got a size. So that's scalars or vectors. Scalars, I hope you get, are going to be easy. They're just magnitudes. Vectors are more complicated, so we need to think about how we can represent them. And the most obvious way of doing it is with an arrow, because that shows me how big it is, which I can show by how long the arrow is, and I can show the direction because it's an arrow. It points. Very clever, you see. It's one of the ways that we are a bit lazy. So we use an arrowed straight line, as you can see, and that gives us the direction, and the length. So we often will take care to draw these to scale as well, because if you can do them to scale, it makes life easy. So that's how we represent vectors. So let's look at combining them, because one of the things we needed to be able to do was add them together. So we'll start with our coplanar vectors, which are ones that act in the same plane. So for example, I've got 2 here which are both acting on the same object and they're acting in the same direction. So that's the same plane. So I've got 4 newtons to the right and 6 newtons to the right. So I need to combine these. So, easy way to do it, if I'm drawing them, is I just draw one, stick the end of one to the tail of the other, and that gives me my new vector. So I've got 4 newtons and 6 newtons, so that gives me 10 newtons. Nice and easy. And if I wasn't sure about the math, which I hope we all would be, but I could have drawn a 4 centimetre line, then drawn a 6 centimetre line, measured the whole thing, and I would have got my 10 centimetres, which would be my 10 newtons. This is where we can scale draw that. So, just a little bit of language. This one I've called my resultant, and the two that made it up are called my component vectors. It's just to help keep you on track and help us distinguish between our two vectors. So, yeah, component and resultant. Now, I could have taken these two vectors and put them pointing in opposite directions. They're still in the same plane, but they're just going opposite ways. So I've now got my 4 newton going to the left and my 6 newton going to the right. And it's this point you can see why direction really matters. Because now when I combine these, I take my 6 newton and I put it on the end of my 4 newton. Well, they're going opposite ways. So when I actually do combine these, I'm going to end up with something smaller. So you could imagine that I would draw from one end of my 6 newton from one end to the other. Then I could put my 4 newton going back, and then it'd be like it just came to here. And that's the bit that I'm going to measure, because I've gone back the way I came. So I end up with a resultant of 2 newtons on this one. Still pretty easy though. So let's make it a little bit harder. Let's have an angle between our two vectors. Let's not be in the same plane, because that's really simple. And also really abnormal. When have you ever come across something that's one-dimensional, that's in one plane? The answer is never. So we're not going to make it that easy. Make it just a little bit harder. Not a lot, just a little bit harder. So let's put our two vectors at angle to each other. So I've picked 4 newtons and 3 newtons and put them at right angles to each other. So here's my right angle, here's my 4 newton, here's my 3 newton, and they're just acting on this object here. So if I want to figure out how these are going to combine, there's a little method I follow. I draw my first vector. So again, my first vector, my 4 newtons. I then draw my second vector with its tail end on the arrow of the first vector, kind of like I was talking about before. So let's just pop it on there. There we go. So that's my 2 vectors that I want to combine. And to find out where they'll add up to, what the resultant will be, I go from the end of the first one, so from the tail of the first one to the arrow of the second one. So just like that. And because, as if by magic, I picked 3 and 4, if I put those into a triangle, into a right angle triangle, I'll come out with a hypotenuse of 5 newtons. It's a very nice Pythagorean triangle. Now I hope you all would know how to calculate that 5 newtons. And if I say that I've done it using Pythagoras, that you all instantly know what I'm talking about. If you don't, you definitely need to ask me, because we're going to do it a lot. But right angle triangles we're going to be looking at a lot over the next couple of weeks, really, and probably actually years, because they come up a lot. So that's how we combine them. So that is adding them together. I can also do this with more vectors, by the way. I could add like 30 vectors if I really wanted, just put them at one end to the other, and then just draw from the beginning of the first one to the end of the last one, and that would be my resultant. So it's quite a useful thing. And the fact that it's, if I draw it to scale, I can literally just measure, which is a valid method in the exam. So I could have, instead of calculating using Pythagoras, I could have drawn a 4 centimetre line, 3 centimetre line, and then measured. And as long as I drew it accurately, my answer would be correct, and that is fine. It can be a bit more time consuming though. So either method is okay, and sometimes they will ask you to draw, so you need to make sure you are happy doing it. But it's easy, like ruler and pencil. Easy peasy. So the last little bit on this one then, and then I will be done talking, I promise, is resolution of vectors. So this is where we take one vector and split it into 2 perpendicular components. So basically it's the opposite of what I've just done. So it'd be like taking that 5 newton and splitting it into the 3 and the 4. And this is very useful sometimes. So I'll show you when it's useful a little later, but just trust me, it will be useful. So let's just think about, I've got a force F, and I am going to split it into its vertical and horizontal components. So I'm going to call its vertical component F with a little subscript V, and its horizontal component F with a little subscript H, because I've gone F into vertical and F into horizontal. It's just a way of labelling them so I can keep track of what I'm doing. So if we just have a little look, oh, there we go. I was going to say it didn't pop up. There we are. Right, so this is my force F here. It's the big long black one. And hopefully you can see that it's inside a rectangle. So we get A, B, C, and D. And the F just goes from one corner up to the other. So this is the force that I'm trying to break up. So to visualize it, the vertical component would go from the bottom of my rectangle to the top, so from D to A, which is the same size as C to B. I'm sure you all instantly knew that, but I'll point it out anyway, just to be sure. And my horizontal component goes from D to C or A to B, which is exactly the same. So if I was combining these two vectors, I'd probably go F, the vertical part, then the horizontal part, and then you can see how that adds up to give me F. All I've done is I've started with F and then split it down into the vertical and the horizontal component. So at this point we can do a little bit of trig, everyone's second favourite thing after Pythagoras, I know. So this angle here is important because it tells me, it'll help me figure out exactly how long the horizontal component and the vertical component should be, because it depends at what angle F is to the horizontal anyway. So if we just look at the triangle, I can say that sine of this angle, so sine of theta, is equal to BC, so this side, divided by DB, the hypotenuse. Yeah, because sine equals opposite over hypotenuse. And that means it also equals DA over DB, because that's also the opposite, because this angle is going to be the same as this angle. Because if you look, it's like Z angles, I think is how they describe it at GCSE, but it's just the same angle. Okay, so I've got two ways of saying it. So that's exactly the same as saying that the sine of this angle is equal to the vertical component over F. So if I want to calculate the vertical component of a vector, I do the magnitude of the vector multiplied by sine of theta, so sine of the angle it makes to the horizontal. Again, I can say cos theta is equal to dc times db, which is equal to the horizontal component times the force itself, times the magnitude of the force. Because cos, as we all know, we do all know Sophie Tower, I'm assuming. So silly old Harry caught Annabelle having tea one afternoon, so caught Annabelle having, so adjacent over hypotenuse. Yes, I do have to say it to remember it. I'm sure you all have your own ones. It doesn't matter as long as you remember. So cos of the theta is the adjacent over the hypotenuse. So that's what this is showing me here. So I can say that the horizontal component, if I just rearrange that, is going to be equal to the magnitude multiplied by cos of that angle. Now that is all actually very easy, and I've probably talked about it so much that I've made it sound harder than it is. So we'll practice in class, don't worry, this is just trig, that's all it is. Now very nicely in your book, in your data book that you get in the exam, they actually give you this equation as well as this equation. But if you can see where it's coming from, it'll be much more used to you and you'll be able to use it a lot better. Right, I hope I haven't confused you too much with that, because it really isn't too bad. And we'll practice, we'll get our rulers out, we'll do lots of scale drawings, and we will become experts at scalars and vectors. Remember, if you've got any questions, make a note, ask me when you see me.